how can we prove that the sum of the interior angles of a triangle is pi radians? Notice, we're not going to think in degrees, and if you don't know why, I will link a video that establishes why. To prove that the sum of interior angles of a triangle, pi radians, we have to take one first principle that we established at the very beginning of trigonometry, and then some first principles from geometry. So I've already explained this in a video. If you haven't seen the video, make sure to follow the card that I will link. But this is called a unit circle, or in general, you don't even have to think of a unit circle, but it's easiest to think of a unit circle. And what we established is a circle, a full spin around the circle, is 2 pi radians. So now that we know a full circle is 2 pi radians, if you divide that by half, that's half a circle. Half a circle is pi radians. So that's the only fundamental thing we need to know from trigonometry. Now, what do we bring in from geometry? Recognize this? Remember this? This is when you have two parallel lines that are intersected by a line. So this line's called a transversal. So you have two parallel lines intersected by a transversal. In this situation, which angles are equal? Well, I gave you two of them. Angle A and angle B are equal. These are called corresponding angles. Now we can find more corresponding angles. For example, this angle and this angle. They are also equal. So we could definitely find more. For example, on this side, right? This angle and this angle also equal. So that's corresponding angles. What other types of angles are equal? Well, the angle opposite of each other, right? So this angle and this angle, opposite angles, sometimes called vertical angles, are also the same. So this angle and this angle, they're equal. Same thing, the angle on the opposite side of B and the angle on the opposite side of A. So vertical angles, aka opposite angles, are equal. What other angles are equal? Well, some people call them Z angles, but usually they're called alternate interior angles. So, on the interior of these lines, on the other side of the transversal, right here, this is equal to B. On the other side of B here, this angle would be equal to this angle. So this is called alternate interior angles. So to summarize, angle C and angle D are alternate interior angles. Angle C and angle E are opposite angles, also known as vertical angles. Angle D and angle E are corresponding angles, much like angle A and angle B. And by the way, if you want extra trivia, angle B and angle C are supplementary angles. Same with angle B and angle E. They're supplementary angles, but we don't have to know supplementary angles for this proof. Now that we've established those fundamentals, let's go back to our circle. Let's draw a triangle that's base is the diameter of this circle, and its two other sides meet at the top of this circle. So let's call this triangle Triangle Kris. Shoutout Kris. So what you notice about this circle is we can have a tangent line, aka a line that touches one point of the circle. And as we go towards the very top, look at the tangent line. The tangent line becomes parallel to the base of the circle. Let's draw a tangent line on the top of the circle that's parallel to the base of the triangle. I might have said base of the circle earlier. Sorry, base of the triangle. I realize now that we also have to know what a tangent is, so you have to pull in more stuff from either algebra or geometry, depending on when you first learned about a tangent. But now we have a tangent line with slope 0, much like the base of the triangle, aka the diameter of the circle. So now, look what we have. Does this remind you of anything? Take a second. Let me extend some of these lines, and you might see what I'm seeing. Do you now see it? Notice we have two parallel lines, and we have two transversals. So what can we do if we have two parallel lines and two transversals? Well, let's apply those first principles from geometry, and we can use some of these angle equivalents to determine which angles match which are equal. So let's do it. So let's start with the angles on the bottom. Which angle is symmetric to the angle on the bottom? Well, using what we know about alternate interior angles, this angle is symmetric to this, and this angle is symmetric to this. So let me draw that. So we now have the two bases of the triangle accounted for up here. What about the third angle? Well, the third angle is conveniently up here. And together, look what they form, guys. Look what they form. It's the angle of half a circle. You can also use corresponding angles, which I drew here. Because these lines are parallel and there's a transversal, that means this angle is the same as this angle up here. Same with this angle and this angle up here. So we've established two of these angles. What about this final angle up here? Well, we also know, remember, vertical angles, opposite angles. So this angle right here is symmetric to this angle right here. So again, up here, we've accounted for all the angles of the triangle. And look at this. What did they add up to? They add up to half a circle. Whether you proved it the first way or the second way, we know that half a circle is pi radians. Therefore, guys, the sum of the interior angles of a triangle is pi radians. Notice we never use degrees because degrees are arbitrary. You can deduce it from the first principles using geometry and a little bit of trigonometry. How'd this feel, guys? How long do you think we can continue not using angles and just using radians? If any of this was confusing, leave a comment, and also make sure to watch the precursor videos, the 2 videos you need to understand this video. Thank you guys so much. Shout out Kris and Jordan and Professor Karla Hoff, and of course Daniel. Everyone's been inspiring me so much. Bye bye.